This is section 1.7, number 3, one of the bifurcation problems. And we're given this differential equation that depends on the parameter a. We refer to the right-hand side as f of y with the subscript a, as this will vary in terms of a. What I recommend when you look at these problems is that you look at it graphically and do a little bit of a parameter analysis with your calculator or whatever graphing tool you want. These pictures are a little bit crude, but here I've taken a from -3, -2, -1, all the way up to 3. And I'll show on the next slide why this range of values makes sense. But first, I just really recommend that you play around. What we're trying to understand is the effect of how, as a changes, the effect it has on the equilibrium points and the overall qualitative behavior of the equation. So I see here at -3 that I have two equilibrium values, one here and one here. I couldn't put too many graphs on, but if I went to -4, I would see a similar type of picture, again with two equilibrium values. The first one, of course, being a source because it's, a sink because it's decreasing. We have a sink here because the slope here is negative, and here is a source because it's increasing. As I change a from -3 to -2, it's lifted up, and we do have only one equilibrium value here, which is a node in that it's positive before it and positive. It's positive here and it's positive afterwards, and so it's a node. And then from -1, 0, and 1, we're clearly above the axis, and so there are no equilibrium values. Everything is positive. These values are all positive, so our phase line would just have an upward arrow. And then we touch down again. Here we have a single equilibrium value when a is equal to 2. And then as we continue to increase, we see that as a is equal to 3, again we have two equilibrium values, which I'll mark here and here. Okay. This is really enough. I would maybe take a look at a few more graphs for me to clearly understand what I'm looking at here. I'm going to draw some phase lines, and let's see how well I can do that. So I'm going to draw, let's see. So what I'm observing is that at a is equal to -2 and a is equal to 2, we have qualitative changes in the behavior of the solutions, because when I'm smaller than -2, I'll always be in a case where I have two equilibrium points. At -2, I have only one equilibrium point, and as soon as I get larger than -2, my equilibrium points disappear until I reach 2 again. At 2, I have a single equilibrium point, and beyond 2, I'll always have two more. And so I'm going to make a drawing that includes these regions. I'll write them in black. I'm going to say here a is smaller than 2. And I apologize for the poor writing. This tool doesn't let me write very well. In fact, let me erase these lines if I can. Nope, I can't. Okay, so one region that I'm looking at is where a is between 2 and -2. And in that region, I see that my behavior is always increasing. When a is equal to 2, here, I have one equilibrium point, which I'll mark in red, and it's a node, and I'm increasing before it and increasing after it. After 2, I have 2 equilibrium points. And so here I'll write A is bigger than 2. And I have 2 equilibrium values. I'll mark them like this. The smaller of the two, this one, is decreasing, so it's going to be a sink. And the larger of the two is a source. When A is equal to -2, I sort of squeeze these lines in a little bit too close. I'll write it up here. When A is equal to -2, again, I have a single equilibrium point. Again, it's a node, and I'm increasing before it and after it. When A is smaller than -2, A is, oops, let's change that to black. A is smaller than -2. I have 2 equilibrium points. The first one, again, is a sink, and the second one is a source. So that's one way of looking at this, and it's my recommended way, really. On the next slide, I'm going to take the same equation and look at it a little more algebraically. So, next slide. And here's our equation again. I'm going to change that color. F at A was y squared minus A times y plus 1. And asking the question, so I want to ask, well, where are the equilibrium points? I ask, well, when is this equal to 0? And I'll find values of y in terms of A. This is a quadratic, so y is equal to minus A, so I have an A, plus or minus the square root of A squared minus 4 AC, but A and C are 1, over 2. And in this case, I can see algebraically the same type of behavior. If I consider the situation where A, so if A is a number less than 2 but bigger than -2, then what I see inside here is that I will always have a negative argument. Let me draw that a little bit better. There. Under the square root sign, if this is a number less than 2 and bigger than -2, this will always be negative. So I will have no real solutions, and so I have no equilibrium points. So no equilibrium points. If A is equal to 2, then under the square root sign I have a 0, and I have one equilibrium point. One equilibrium point when y is equal to A over 2. And this equilibrium point, I'd have to do some analysis to realize that that's a node, but just notice how the numbers change. And when I'm bigger, if A is bigger than 2, then I have 2 real roots, 2 equilibrium points. Moving in the other direction, and that'll stay true for all A bigger than 2, and moving in the other direction when A is equal to -2, I only have one equilibrium point. And when A is smaller than -2, again I have 2 equilibrium points. So I'm taking all of that information from this equation. I would still want to know, well, at this one equilibrium point, if it's a node, it's obviously not necessarily a node, but I'd have to determine that this is going to be a node. Here I'm going to have a source and a sink. Here I'm going to have a node again and a source and a sink. And so at some point I need to go to the graph or do some other analysis. But this is a perfectly good way to do some reasoning. I certainly recommend the previous slide. Do a little parameter study, look at the graphs. The types of pictures we're going to have will be such that the graphs will reveal what you need. So the picture on the previous slide is what we want. The 6 lines that were drawn that show the behavior of the phase lines for the different values of the parameter A is all that's needed. I hope this helps. Good luck. Bye-bye.